Hello, I'm Roman, and welcome back to the series of the videos Neural Networks from Scratch in Go. And if you watched previous videos, you can see the main visual difference. I switched to the dark theme on the laptop. And the reason to this, well, I'm doing this back and forth from time to time, but on the previous video, one person commented that he or she closed the video because it's not that comfortable to watch live coding videos with light theme. And then I actually asked in the community section for this channel if there are people who would prefer dark versus light. And suddenly, for my small channel, several people answered, so it looks like most of the people would, for most of the people it would be easier to watch my videos with the dark theme. So I change it for a week, and I will see, because I have my issues with the dark themes on the macOS in general, but I will try it once again. Also, you can see that there is and one of the things that the book is still white, so anyway, you will see that there is this split between the light and the dark on the same screen. From time to time, I will make the terminal window bigger, but yeah, we'll see. And there is one more thing. You can see there is a QuickTime view that shows currently it shows my iPad, and I want to use it for today's video because I want to draw some things. And previous video is titled Being Stupid and Not Productive. That's what actually happened last time. I'm trying to implement the backward pass for the dense layer, and there is clearly some issue with how I wrote it, because for example, that calculates correctly, but on the gradient on the input there is some issue, basically the mismatch between between matrix dimensions. And I'm using the example from this book. I think this is I'm trying to replicate this example, but with no luck so far. So I want to draw some things, because for me it's the best way to actually, put everything in order in my mind. For example, here I'm still confused. There is a d values, but then suddenly we're using the copy of the real output as derivative from the previous next layer. So let's see. One of the things that in the dense layer I want to change in the initialization mode, I just want to make sure that I doing everything correctly. So for example, I think somewhere it was written that we are storing the weights transposed. But for example, if we take a look at the code that is listed for the dense layer, it doesn't look like this, because for example, we initialize the weights as random or as inputs and neurons. It's the numbers I have the same, and bias as we create in it's called column vector. So we have one column with lots of the rows. Oh, actually it's vice versa. NP zeros. Zeros. This one. Return a new array of the given shape filled with zeros. For example, we have 2. So we have 2. No, okay, so in that case we'll have one row with the columns, And I think the main thing that we will use the column index to access actual values. So this is basically the same. And for example, if we're taking the matrix multiplication, we have two matrices. The first is, well, m multiplied by n, and then we multiply it by n multiplied by p. Those are dimensions, and this should be the same. And I have the problem with one of the, I think, the backward pass for the inputs, that it's not the same, and the result, so that should be the same number. If the number of columns and the number of rows between the matrices is different, then there is, well, the matrix multiplication is not possible. And the result matrix will have this dimension. So we're taking the number of rows from the first matrix and the number of columns from the second one, and this will be our result. And to make more consistent, and since we are storing, I store not transposed weights, I think I need to comment. For example, weights has rows, for the weights, it's defined number of neurons within the layer. It calls number of, oh, actually no, I have it number of neurons, number of inputs, and here it's actually wasn't correct, so I do store it as transposed, right? Maybe I shouldn't, because I'm, personally I feel a little bit confused with these things, because for example right now, okay, let's do number of rows and number of inputs from previous layer. That means here I will so if we'll store it like this, so we store it as not transposed, but here we store it as one row with calls equal to number of neurons. Okay, and that is already confusing. Maybe actually my issue here is that it should be transposed here already. So let's, because the biases we store as one row where every column value the number of neurons, right? What it means? It means that we will have for the biases Okay. For the biases, we will have something like this. And if you want to get the corresponding value for one of the inputs, we will do 0 and then index of inputs, right? Okay, what if we will go with approach that is here? So that will be number of columns, that should be number of rows, and we exchange it. And then I will, do this. Number of neurons. It means that we storing weights in transposed way. So we already transposed it. And same for biases. Storing kind of. What it means? It means that we already can, I will delete this number of rows. For example, we have inputs. Let's take a look at the so for example, we have the input of 2, so we have 300 rows, but it's not that important. The important thing that we have 2 values, x and y, and the size is 300 by 2, and this is the important part. So we have 2 inputs, then we have the first layer of how many? What is it? Number of inputs and number of neurons. So we have, this is the input, right? 1, 2. Then we have number of neurons, 3. This is the first layer. Means that we have 1, 2, 3 weights. Right? So for example, this, if I will go with one, that will be, for example, x, y multiplied by, we're storing in transposed way. So we have the matrix where the number of rows is 1, 2, 3. So it's 3 multiplied by 2. And this 1 is multiplied by 2. And in order to have the And in order to have the matrix plot, we need to transpose it. And this is what I had, but in that case, I mean, why do I need to... I mean, it doesn't make any sense. Why previously we had to transpose it in this way? I think this it was here, right, where we wrote first dance. We have weights, number of neurons, number of... Where we had it is... We had the transposition here, right? Okay, for example, we have... Considering this one, we have 4 values as an input. We have 4 weights and 3 neurons. The number of... Okay, so the idea was that we store it here as each row corresponding to each neuron, right? And by transposing it, we have 3 by 4. When we transpose, we have 4, which is the number of inputs. Okay, let me just get back full code. With 2 inputs featured and 3 output values. Okay, so we have number of inputs, number of neurons. Let's do it the same. Oh. Number of inputs from the previous layer. Number of inputs, number of neurons. Okay, let's take a look again at this example. So we have number of inputs, in this case 4, number of neurons 3, but here, okay, so in our case each column corresponds to weights, so each column corresponds to weights of each column corresponds to the weights of the... So it, for example, it will be like this multiplied by, if I change this example, it should be, so this is the first 0 neuron, this is the second, and this is the third. Okay, this is what I... So this will be our multiplication, right? So if we take a look, if number of neurons, number of, and in inputs, okay, this number of rows number of rows is equal to batch size to input sample size, right? But then we should do no. So we are storing it already in a way where so the weights are already transposed and prepared for, where is it? And prepared for this multiplication. So if we take a look what we're doing, we've taken the allocating the result, which in our case, for example, here it will be this one multiplied by 2 by 3. By this one it should be this 1 by 3. So we're taking the number of rows from the input, which corresponds to the number of samples. For example, if we're going through one pass, that will, well, if we're inserting one input, that will be one row, but if we have multiple, then we have multiple. So that should be the result product. In that case, we should have 1 by 3, because we already storing it in the transposed way. Then we do the product, and what we're doing next, we're taking the next thing we want to do, we want to sum these things respectfully, right? So we want to have for each output and every so the output is rows number of inputs from previous layer, k number of samples, columns, number of neurons from the current layer. So here we should have 1 by 3, because we're going, well, in this example we have three neurons, that we should have 3 outputs for each sample. 3 outputs for each sample. Okay. And what we're doing, we're going through the result. We're going through every row, which is actually going E sample number, and we add biases. And that will be our result. So the result is having calls where having calls with neuron Okay. Then here pretty much the same with the loss. It's pretty much the same because, and with the softmax it's pretty much the same. So how are we going to test it? We have, I think, we have the run model, the one that I implemented first. Let's, draw it. So we have 300 rows by 2. So the model is, we have 2 inputs. This is, inputs. We have 2 of them, and they stored as columns. So input 1, input 2. Then during the initialization, we define number of inputs, so that corresponds with this one, and the number of neurons. So we have 3 neurons. This is the layer 1. Then we have on the layer 2 we have 3 inputs that corresponds to this one, and we have again 3 outputs. So how it will look like? We have this is the first, and we have it has 9 connections because it's the dense. Okay, so how this is going to be? So we have, for example, if I'm going with one input sample. So I have one row with 2. Maybe actually, it will be easier to understand if we go with like this. This is the inputs, then we have layer 1, then I have layer 2. So each column represents the value from the neuron. Probably that will be easier for me. Well, the column represents the neuron, and the number of rows represents the number of the weights, which is equal to the previous number of the previous. So for this one we have 1 by 2. Then we have two inputs, 3 neurons. So we should have 2 inputs. So we have 2 inputs. It means that we have two rows and 3 columns. So first set of weights, second, third, and the result will be 1 by 3. So we had, in the beginning we had 1 sample for, I should change the color. So first we had two values for the layer, for the input, then we have three values. So we end up 1 by 3. And then we multiply it through, well, three by 3. Here it's harder, so this one 1x3, and here it's 1x3 multiplied by 3 by 3. So this is the first neuron that is connected with all three inputs from the layer 1. This is the second and this is the third, and we will have again, after transformation, we will have 1 multiplied by 3. That should be the result. So the result, the output is always number of inputs by number of neurons, right? I will try. It should work. Yes. So it works. What about the second one? Okay, it works too. The accuracy is the same. Okay, so right now, my biggest problem, I think that, yes, it has an error. But what I'm doing incorrectly, the main thing, where is that propagation? I think the main thing is how we should go back, right? Let's take a look at the example once again. So we have inputs 3 by 4. So we have actually, so the idea of the backpropagation is that we go in this direction. Oh, sorry. We forgot to change it. Okay. So the idea of the backpropagation is we go in like this. Or actually, if, you know, if I would consider this way, so it's kind of going up. And what we have here, okay, so where is it? So we have the D inputs. I kind of feel like the main problem is that I just declared manually the weights incorrectly, because the way they store it here is corresponding to the inputs, but we store it in a different way. And this is why maybe I got confused. But okay, so 3 by 3. Okay, let's take a look. So here we have 3 by 4, right? 1, 2, 3, 4 multiplied by weights, transposed weights, which is 4 by 3. That gives us 3 by 3. Right, so we have layers output, ReLU output, just call it maximum, it's still 3 by 3. Then we're making a copy. Okay, so the DReLU. Okay, so in this case, the ReLU has 3 by 3 dimensions, where 3 is the number of samples and 3 is the number of neurons. So that should be like this. It's the relu. Right. Then we calculating the inputs, and let's optimize and test backpropagation here. Relu activation simulates derivative with respect to input values from the next layer past the current layer into backpropagation. So we're assuming that we have again 3. Okay. So we're assuming that we still have this 3. So this is the inputs and the weights 3, and here we have 4, right? Because the number of weights is defined by the number on the previous one, and here we have 3 neurons. So this is the DERO, this is the inputs and weights, right? In that case, the input, since our weights are, this is the weights, is 4 by 3, and we're transposing it again, so we have the D input as 3 by 3 multiplied by 3 by 4. So we should have 3 by 4, right? This is the D input, and if I take a look at the D input array, this is 3 by 4. Okay, so what I'm thinking about this. First of all, I think the problem with this example, because the weights should be 4 by 3, oh no, 3 by 4, and they should be transposed because of the way this example is done. Since I have troubles to do this, what I'm going to do, I'm going to copy the weights transposed. I think I copied this one. Okay, so that would be okay, so I should store it like this, right? Weights 4 by 3. Okay, so I have, this is the first, this is the second, third, and last one. And I removed this, so we have 4 by 3. Okay, let's check. Declare but not used. Okay. I want to check that. Okay, forward pass actually works. Okay, then let's check if the activation backward pass works. Okay, then okay, mismatch. Probably this is correct right now. what we're going to do, since okay, where is it? This one. Okay. So the input is what I'm correcting, what I'm correlating first. Gradient and params. Okay, let's do one by one. Gradient on inputs. Okay, let's. Rearrange a little bit. So we have d values, and we need to transpose again. So we have 3, for example, we have 4 by 3, then we need to have 3 by 4. It means that here we should have 3 by 4, I think. Okay, so the dimension mismatch is already here. Okay, we taken transposed one, and then yes, we should transpose it here. Okay, then we have gradient on params. So the next one is we calculating the gradient for biases, and I think this one is pretty much the same, where we're taking the number of rows from the d value because it corresponds to the number. Oh no, wait. We have the d values. We're taking the derilu and we're summing across first chapter of chapter. We have the derilu. We have the sum. So we're doing sum across columns, which means that we have the same amount of the columns as we had rows. Okay, so that's okay. This is one the same, and then the third one is gradient against input. So we're calculating the d weights. And what we're taking the transposed inputs. So the inputs actually from previous layer. So it should have four rows, right? No. So we have 3 by 3. No, wait. It's the inputs shape 3 by 4. So yeah, that should have 4 by 3. Why the inputs had 3 by 4? Oh, yeah, that's correct. Yes, so the inputs, we have 4, and this is because, well, those are the inputs. So we have 4 of them, right? So this is why we have the weights 4 by 3, but transposed back, so it's 3 by 4, right? Inputs T shape. Oh, 4, right, 4 neurons, 4 columns transposed that we have, yes, 4 by 3. And then we multiply it by the D value, which is 3 by 3. That should give us 4 by 3, right? So what we take in? We take in the number of rows from the inputs, transposed inputs. We take in number of columns from the D values. And then we take in the product. Oh, if it's not going to work, then I have no idea. Okay. And it looks like the correct answer. Yeah, I need to check answers here. So we print in the inputs, print in the weights, and the biases. No, still incorrect. Oh, but I guess I'm using the different values, right? But I'm using the relu copy, but here relu copy, so the D values actually met copy, dense copy of active page out. Right? Yes. Yes? Okay, so that was the issue with, I mean, okay, this example was really confusing for me, especially with this, you know, we declaring the D values, but suddenly we're not using it, and it was a little bit hard to evaluate it. Okay, so I'm checking the results, and actually, so I finally, I've tested the backward path for 1 layer. That should work for the 2 layers the same. The main problem that I had is, well, a little bit messy. The main problem that I had was actually messy declarations, and, you know, I was a little bit not confused, but, well, yeah, the way I'm storing things everywhere. But right now it's more clear, especially, well, I have the comments, which is good, but for example, taking the rows and columns for the result matrix is always written in the same style. So we're taking the number of rows from the first param from the dot product, and we're taking the columns from the second param from the dot product. The main thing is, for example, if I need to transpose something, I need not to forget it in 2 places, or I can store it in a separate variable. So for example, I have the forward, I have the backward pass. Let me clean this and this. I don't need it anymore. So for example, yeah, for example, we are transposing it and here. And yeah, finally it works. The next time I finally will go for the categorical cross entropy loss derivative and implement this. And I think there are a couple of the derivatives that I need to implement still, but it's good that, you know, I finally put all of the things inside my head and properly refactor the code. So that's the good thing. And yeah, this is an example when you know, stuck with something, and it's always good to dive into, you know, slowly dive into some things and get to the point of where you're wrong and what you're missing. And sometimes even starting from the beginning, you know, from the scratch helps. Here, I didn't have to do this, but I spent some time and now it's much better. For now, thank you for watching and I see you tomorrow. Bye bye.